chat about additive systems. So this is a topic that I wrote a paper on a couple of years ago. I was made familiar with it a couple of years earlier with an interesting paper I read. And I find it just an engaging topic that I hope to let you know something about. So before I tell you what an edit, so by the way, I'm using a Jamboard, and in case anyone wants to look at the Jamboard itself, I'm going to post the link to the Jamboard in the chat window. And of course, whenever you want technical stuff working, I can't find my chat window is not coming up. Yeah, I've never had that problem not pulling up chat. So, okay, I'm gonna briefly stop sharing so I can do what I said I would do. There's the Jamboard that I'll be using. And you're welcome to go there, although if you page along, you may be at a different page, so it might be easier to just look at the screen, but either way, you can be looking at what we're doing here. Okay. So before I tell you what an additive system is, I'll just basically give you a couple examples, and I don't know about you, but I always prefer actual interaction, and I can see all of you, but I may call on you, just sort of randomly for one or two things just to talk about. So the idea of an additive system is that we're going to take a sets of positive integers, and so the first one we've got here is one set is the integers from 1 to 9, the next is 10, 20, 30 up to 90, and then 100, 200, 300, 400, and there's really no mystery as to this pattern, and this goes on forever, so these are infinitely many sets, and the next one obviously is 10,000, 20,000, and so forth. And the idea, again, is nothing particularly difficult. If I give you if you give me a positive integer, I don't know, Sungwon, give me a 6-digit positive integer. You have to unmute yourself.
6-digit, 1, 2, 3, 4, 5, 6.
Sounds good. No arguing with that. So the idea is that no matter what number you give me, what positive integer you give me, I'll be able to make that number by taking, oops, fix the Jamboard a little bit. I'll be able to create that number by taking at most one number from every set and adding it. So I'll certainly take 100,000 and I'll add that to 20,000 and I'll add that to 3,000. And I'm having a little problem with my keyboard. And 400 and 50 and 6. And obviously these add up to the number that Sungwon gave me. But the point here is that I'm using at most one number from every set. And I'm only able to do this in one way. If you give me different numbers from each set, this is the only possible way to get 1, 2, 3, 4, 5, 6, is to do it exactly this way. And again, just to sort of, I'll just take a slightly different number. And I'm doing this only to demonstrate that we don't need to take something from every set. I obviously am not going to take anything from the set that includes the thousands. So there's one and only one way to do this. And this particular group of sets that I have is obviously based on how we write numbers in base 10. And what I've got below is that we could do exactly the same trick, except we would use binary numbers. So instead of having 9 numbers per set, if I use binary numbers, I'm only going to have 1 per set. I've got 1 and 2 and 4 and 8 and 16 and 32 and so forth. And I don't know, Jimmy, give me a number that's not too large, maybe close to 100 or 1,000 or something like that. Oh, you're going to have to unmute yourself, however. Either that or you can sign it in the window there.
Right. 365.
Sure. So how are we going to make 365? Someone unmute yourself and tell me how we're going to do 365.
Yeah.
It can be Jimmy or it can be anyone else. And you might think about what's the largest power of 2 that you could take away from 365 without going negative. Anyone's welcome to chime in here.
Yeah, I'm drawing a blank.
Someone help Jimmy. 256. And so if we subtract off 256 and my arithmetic works out, I think we have 109 left over. So to make the 109, we'll take, what's the next biggest power of 2 that we could take?
64.
64. And what do we have left? 109 minus 64. Uh-oh, I think we got 45 left.
Right.
So to make 45, I'm going to use 32. And that'll leave 13 left. And so I'll use 8. And that'll leave 5 left. And I can do that with 4 and 1. So one of the nice things about this, and I hope that my arithmetic's right, and otherwise I hope you'll excuse that and understand that the pattern will still work. What's nice about this is that not only can I do this in one and only one way, but I have a nice little algorithm to make this happen, which is that in both cases, both of these examples of additive systems, we can make this sum in the one and only one way by taking the largest number that appears in any of the sets. So in the case of the first one we had, 1, 2, 3, 4, 5, 6 here, 100,000 was the largest number that appears in any of these sets that is no bigger than 1, 2, 3, 4, 5, 6. So I use that as my first number. It's sort of a greedy algorithm. I take the biggest thing I can, and then with 2, 3, 4, 5, 6, 20,000 was the next biggest number. And then I'll take 3,000, which is the next biggest number that's left, and so forth. So what do we mean when I say these words additive system? I should actually give you a definition, and so I'll do that. And this is just a little bit big. There we go. So we can have additive systems of infinite or finite size, and the distinction is a fairly small one. But the idea is if we have an additive system of infinite size, it's the examples that I was showing you in the previous slide, where every non-negative integer can be realized in one and only one way as the sum of some numbers from the collection with no two numbers from the same set. And that's exactly what we were describing. And a slight variation of that is an additive system of finite size. And the idea there is we're going to, again, have a collection of sets, and we're going to call it size some number z if we can write all of the non-negative integers up to but not including z as exactly this sort of a sum, one number from each set, at most one number from each set. So for example, if on this first decimal example here, I took only the first 3 sets, that would give us an additive system of size 1,000, because using the first 3 sets, we can create all of the non-negative integers from 0 to 999. So we call it of size 1,000, which is a nice rounder number than calling it size 999. But we call it of size 1,000 because we have 1,000 numbers we can create. We can create anything from 0 to 999. Similarly, on the second example, if I use the first 4 sets and not all of them, that would be an additive system of size 16. Because if I use the 8, the 4, the 2, and the 1, that gives me 15. And so all the numbers 0 to 15 gives me an additive system of size 16. So let's look at a couple other examples, or possible examples. And before I sort of ask you whether this is an additive system, let me explain my weird notation here. So this potential additive system is only 2 sets. And the first set, when I write zeros with question marks here, that's just my own little notation. But the idea is I want to describe all the numbers that can be written in decimal form where all of the even digits are 0. So for that particular example, and let me get something a little smaller there, for an example of something in that first set, oops, there we go. would be something like, yep, something like, so the tens digit is 0, and this two more digits over is 0, and this is 0, and that's 0. And the question marks can be any digit 0 to 9. So that's what I mean by numbers in the first set. And similarly, the numbers in the second set are going to be the numbers where all of the odd digits are 0. So something like that. So the first, third, and fifth digits from the right are 0, and so that would be an element of the second set. So Mishi, give me some arbitrary number, pretty large, lots of interesting digits, just so we can take a look at that.
You mean one that follows this second notation?
I actually want just any old number as random as you can make it.
I mean, I guess I'll just start listing digits then.
Sure, great.
6, 4, 1, 7, 8, 3, 4. I'm not sure how long to make it.
Maybe 2 more digits.
Okay, 5, 0.
Great. So how do we write this? So if this is supposed to be an additive system, and that's what we're trying to determine here, we want to know whether this number can be written as the sum of 2 numbers, at most 1 from each of these 2 sets that I've described. Either Mishi or anyone else want to give it a stab at it?
I think you could do it if you, I mean, the I'm not quite sure how to describe it, but just.
Well, can you give me the two actual numbers?
Oh, okay. So I mean, I guess we would have 6, 0, 1, 0, 8, 0, 4, 0, 0, and then 4, 0, 7, 0, 3, 0, 5, 0.
And I wasn't looking, I had to type instead of looking, but I feel fairly confident that you did that exactly right. And so there are 2 things we need out of an additive system. One is, does everyone agree that we can take any non-negative integer and break it down as the sum of at most 1 number from each set? And the -0 here is just indicating that I'm not allowing 0 to be in either set, but that's okay because I don't need to take anything from either of these sets. And we also sort of have a good enough feel for numbers that this is the only way, for example, that we could have gotten Mishi's original number of 641783450. There's no other way to do it using 1 number from each set. Okay, so answer to our question? Yes, this is an additive system. And I'm not going to sort of give a formal proof here, but that probably is a reasonable statement to make here. How about this one? Let's ask the same question. Is this an additive system? And we can start off with something of the same sort of thing, which is, well, let's just take a number, maybe not 8 digits long this time because the numbers are a little smaller in this case, but let's give it a try and see if we can figure out why it is or why it isn't an additive system. So, Misha, I picked on you this time. I'll ask for volunteers, otherwise I'll pick on someone else. Someone willing to step up and first of all give us a number, and then we can talk about whether that number is expressible in one and only one way. Steve, I haven't heard from you.
Okay, 23246.
Great. So, any ideas about how to start, Steve?
So that last set that just goes on forever?
Yes, it does.
Going up by hundreds. So then presumably it gets up. So then it would be 23,200.
Great, because using that greedy algorithm that I was talking about, that's the biggest number we could pick.
And then
We
I
still
guess
have to account for 46.
then 25, 20, and 1.
So I totally believe that that is equal to 23,246. I don't think anyone objects to that. Is this the only way that we can create this number? Will, you're shaking your head. Can you give us a reason why there are other ways?
And 46, I could do the 23,000 plus 20 plus 15 plus 5 plus 4 plus 2.
I think I need you to tell me that again so I can write it down. I wasn't typing.
20 plus 15 plus 5 plus 4 plus 2.
Okay. This is not a counterexample, but we need to look again at the definition of additive systems to see why. So let me remind you that when we talk about an additive system, we're talking about writing these numbers as the sum of numbers from the collection with no two numbers selected from the same set. And you violated that rule because 20 and 15 are in the same set, 4 and 2 are in the same set. Okay, so we're not going to allow this particular sum for that reason. That doesn't mean that it's an additive system. It just means that that particular example isn't a contradiction. Is there another way to write 23,246? And I think the fact that we're all sort of silent here indicates that there's something weird going on, and maybe it's not obvious whether this is or isn't an additive system. So let me give you some hints here. What if I write some helpful words like I call this set pennies, and I call this set nickels, and I call this set quarters, and I call this set half dollars, and I call the last set dollars. So again, the question that we're asking here is, can we express every non-negative integer in one and only one way, using at most one number from each set? Like, where did we get the 46 here? We got the 46 in this example by taking, how do you get 46 cents in US currency? Well, we take a quarter and we take 4 nickels and we take a penny. And if I limit your use of US currency to pennies, nickels, dollars, half dollars, and dollars, it perhaps feels a little familiar. And I'm not giving you a proof here. I will be straight up. We're not doing proofs right now. But I wanted you to get a feel for it, which is, I think, far more important than a rigorous proof, which exists. But yeah, we're going to take, that's how we get 46 cents. And let's not worry about the hundreds, because we could just use as many dollar coins as we wanted. But I don't know, someone throw out a different number. Jorge, how about giving us another number? Let's just think about it. You're still muted. I didn't get you. Sungwon, give us another example. Something to work on here. Just another number to start with.
Maybe 1,352.
Great. And thinking along the same lines, if I want to make $13.52, I would probably use $13 in dollar coins And to get 52 cents, I would take a $0.50 and 2 pennies. So it seems, oops, sorry. It seems that the answer to this question is probably. Is it an additive system? Well, probably. I'll spoil the surprise and I'll say, yeah, there's a rigorous argument there, but before we get there, let's look at this slight variation. And if we let me rewind just a moment here. If we think of the sets here as follows. If I'm trying to make a certain amount in dollars and cents, like $13.52 or $232.46 in these two examples, 1, 2, 3, 4 is the value I would have when of the pennies that I use. I could use 0, 1, 2, or 3, 4 pennies. And then I'd use I'd use 0, 1, 2, 3, 4 nickels, so the value would be 0, 5, 10, 15, or 20 nickels that would be the value of the nickels. I'd never need more than 1/4 because I'd use a $0.50 if I needed 2 of them. So 25 is the only value I'd use for quarters. 50 the only value for $0.50 because then I'd use dollar coins, and I'd use as many dollar coins as I needed. And we're getting close to a proof with that argument. But let's not try to be, quite so rigorous and get the idea of what's going on. What do I have here? I really have the same picture thinking of US currency, only now I've got a pile of pennies, nickels, dimes, quarters, and I dropped the $0.50 because I was bored of them, and the dollar coins. And if you've made change in US currency, you'll know that you'll never use more than 1 nickel. You'll never need more than 1 nickel if you're trying to make change as efficiently as possible. You'd never use more than 2 dimes because you'd use a quarter. If you need 3 dimes, you'd put a quarter and a nickel together, and so forth. Is this an additive system? Same question. Melanie, your thumb is down. Can you tell us why?
5 plus 20 equals 25.
Sure. So just simply the fact that we could make 25 in these different ways. And let me make the example. You gave a very efficient example. I'm going to change it just slightly because I like to think about, well, if I wanted 26 cents, I could use a quarter and a penny, or I could use 2 dimes, a nickel, and a penny. And this is most definitely not an additive system. 25 was fine. I just think this is, for those who didn't see that example immediately, I think it's easier to see 26 than 25. Not an additive system, and that's why. So a little bit of history in the, I should have had this date on the tip of my tongue, but I think it was in the 60s. De Bruyne wrote an article about additive systems and stated a fact about how additive systems can all come about in a certain fashion. And then I got introduced to additive systems when Mel Nathanson wrote a later article. It was published, I think, around 2013. And Nathanson's article basically provided a full proof of De Bruyne's theorem. De Bruyne had some reasons. So I actually had some interaction with Mel Nathanson a couple of years ago. And when I read De Bruyne's theorem and Nathanson's follow-up article, my reaction was, oh, De Bruyne didn't actually provide a proof. He left out so many details that didn't really constitute a proof. Nathanson didn't exactly feel that way, but maybe he was just being modest. He felt like he was just fleshing out the arguments that were already there. I myself didn't see those arguments and couldn't find them in De Bruyne's very short paper. But both of them together said, there's this way that you can create an additive system, and I'll be describing that in just a minute, or a slight variation. And every additive system comes about in this way. And by the way, that even goes for systems that are really weird, like this one. Oh. And I realized that I just spoiled, okay, I gave you something out of order because I should have looked at the next slide first. We're going to get to that structure theorem in a minute, but we're going to get to an example that will motivate that a little better here. And I'm going to go through this a little fast because I already moved to the next step in my head. But it's probably not clear. It's probably clear that this example looks rather different than the ones with pennies and nickels and so forth. And it's probably not so clear whether the answer is yes or no. I'm going to give you just a moment just to think about whether this or why this is an additive system. I will tell you this is an additive system. And I'd like you to think for a moment about that. And I apologize, I'm going to have to take this off the screen for just a moment, but as a motivating factor, I want to put that nearby the example from the previous page. The one with, sorry, that was the wrong one. The example from 2 pages ago. So this was the example, this was our example from 2 pages ago that was an additive system. Does that help you see why what we're looking at on here is in fact an additive system? Does anyone want to try to explain it? Well, give it a try, Melanie, please.
So if you have a number and you look at it mod 5, if you get something that's like a 1, 2, 3, or 4, you're going to use one of the beginning thingies, either like the 1, 2, 3, 4, or the 51, 52, 53, 54. But that's not really enough because you also kind of have to look mod 50. Not quite mod 50, but like at what's happening in the 50s place. You can't really get up to 50 without using one of the 50, 51, 52, 53, 54s, right? Because the others, the little bits like, I guess if you take it mod 100 and look at what's remaining, everything bigger than 50 is going to have to use one of those 50 bits, and everything smaller is going to use one of the other bits. And the 25s will either put it in a regime. This is not a simple answer. The other one had a simple answer.
Well, that's
Michael,
okay.
this one is a complicated answer.
But it's got all of the right elements, and so let me just help you clean up the ideas that you already have, because you're really,
it's sort of the 25, like the 0 to 24 regime, or the 50 to 50, you know, 25 to 49 regime, or the 50 on regime, or that sort of tells you which half of the first set or which half of the second set or third set you use, and then you've got that middle bit.
Yeah. So really sort of what's going on when you're saying, you know, I'm going to go mod 5 or mod 50 or mod 100, you know, you're sort of trying to cut things off at certain points, and that's a good instinct. And another way to think of that is it's almost like we're working in, you know, base 5, base 7, base 20, only we're sort of mixing our bases together. You know, it's almost like if you look at this example, our earlier example, it's like we were starting on base 5, we got 1 through 4 and 5 through 20, except then all the things sort of change. And sort of what these additive systems sometimes do is they're sort of like they're mixing different bases with other bases. So if you grant me, and I hope you will, that this lower system is an additive, this lower collection of sets is an additive system, let me give you a cleaner argument, but basically along the same lines of what Melanie was saying as to why the top one is an additive system. In terms of the lower system, if I give you a dollar value, dollars and cents, these sets tell you how much is the value in pennies, the value in nickels, the value in quarters, the value in half dollars, the value in dollars. And you could think of some cashier with 5 different drawers, and there's the amounts of money that comes out of each drawer. Well, what if our cashier, instead of having 5 drawers, had only 3 drawers? And one of the drawers held the pennies and the half dollars. And one of the drawers held the quarters and the dollars. So just to give a little coloration here, so I'm going to put red for the, oh, let's make this a little wider.
That's a pointer. The top one's a pen.
Thank you. I don't use Jamboard enough. And I'm going to make it red. Thank you, and something nice and thick. So if I make dollars red and quarters red, I'm putting both of those into this drawer, and those are the values that can come out if, because we could only use at most 1 quarter and at most, and any number of dollars, and that's how we get those values. Whereas I'll color the pennies and the half dollars blue because those are combining to make this set. And then, and of course, if if these terms mean something to you, what do we've got? We're really partitioning the sets on the bottom with one of these 3 colors, and each equivalence class in that partition is giving us one of these sets. And I hope that that's it's a nice hand-wavy argument about why the top one is an additive system. I also want to make another point, which is that only some of these sorts of mixings are going to be useful. Like, what if I put the quarters and the half dollars in the same drawer? Well, then we could make 25, 50, and 75, and it's almost as if we just had quarters and no half dollars. So if we mix these things together, if I had colored any 2 adjacent ones the same color, that's sort of a boring case. Mixing together the nickels and quarters, I get 5, 10, 15, 20, 25, 30, 35, 40, 45. And that's just as if I'd had pennies, nickels, but no quarters, and then half dollars. And that's going to lead us to the structure theorem. So what I did in my paper is I refined the definitions, changed really the definition of some of these terms so that my structure theorem, as opposed to what De Bruyne and Nathanson did, guarantee not just that there is one of these ways to create these additive systems, but it gives us a unique way of doing it. And of course, that's a much nicer, cleaner result. So the examples that we have, like for instance, when we took this system on the bottom and created this system on the top, I've got another example here just to get the idea. And what we've got on the left are called British number systems. And De Bruyne invented that term because, unlike today, back in the 60s, the British system of pence and shillings and pounds, there was, what, 20 pence to the shilling and 12 shillings to the pound. So it was this sort of mixing of different bases. It was almost like base 20 becomes base 12. And that was his idea about what a British number system. And these are the sorts of things we've already seen, where maybe we've got 1, 2, 3, 4, and 5, 10, 15, 20. Oh, it is the example from before. I'm sorry. I forgot what I put on this slide. But notice what happens. We're starting with 1, 2, and up until some number. What starts the next set? Well, the next number that's missing. And then we count up from that number. So we certainly don't need 5, 6, 7. The next number we need is 5, 10, 20, because with just this 5 and the 1, 2, 3, 4 above it, we get 5, 6, 7, 8, 9. So the next we need is 10, and then 15, and 20, as many as we want. And then the next set down starts off with the first number that's missing. And this would be 25, 50, 75, or whatever, but the next set starts with whatever's missing. And we could also have a set that's infinite. That was one thing that De Bruyne and Nathanson didn't allow, and that's part of why they didn't have a uniqueness result, is they didn't allow sets like this. And I realized, well, if you allow sets like this, that's going to be one advantage and help us get a unique system. And the other thing is that in my definitions, I distinctly disallowed coloring 2 things that are adjacent with the same color, because those are boring examples and they ruin the uniqueness. But if you change things to only allow those sorts of mixings, or what I called quotients, So the terms don't matter, but the system on the left is called a British number system, and the system on the right is what I termed a mixed quotient of a British number system. Quotient indicating that I've colored the sets, and mixing indicating that I have deliberately not colored two adjacent sets with the same color. And so the structure theorem says every additive system can be uniquely expressed as a mixed quotient of a British number system. One thing I want, so there were some related results, and I don't need to go into all of them, but to sort of connect with some of the things we were talking about earlier, let's look at this system on the right. And one thing that happens when we create these quotients, these mixed quotients, is we do ruin one of the properties that we talked about earlier. On the system on the right, someone tell me how we make 57. Don't be shy. It's not a trick question.
52 and 5.
Sure. And why did I pick this example? That you're exactly right. This is the one and only way to of course I have to write it correctly. This is the one and only one way to write 57. But why did I show you this example? What was our previous method for finding how these numbers are written? We used that greedy algorithm, right? Do you see the greedy algorithm fails? The greedy algorithm would tell us that we have to start off with 54, the biggest number that's available. But if we start off with 54, we're in trouble. There's no way to make the 57. So a related result that I had was that greedy algorithm works if and only if we started with a British number system. If we take a mixed quotient, for certain numbers that greedy algorithm might work, but it does not work for all.
In which sense what is the mixed quotient? I think
Sure. Yeah, no, that's fine. Please let me say that again. The idea of the mixed quotient was to start with one of these British number systems, the idea of 1, 2, 3, 4, and the next set starts off with what's missing and counts up by those multiples, and that process continues. And the idea of the mixing quotient is what we did here, where I take a British number system, that's what's on the bottom, and then I just simply, let me not say mixed quotient, but let me first say what I mean by a quotient is I'm going to color each of these sets, make a partition basically. And any two sets, with all of the sets that have the same color, like for instance the half dollars and pennies, I'm going to create a new set with that color that lists all values that can come from using those two sets. I could use nothing from 1, 2, 3, 4. I could use nothing or 1 or 2 or 3 or 4. I could use nothing or 50. And those give me the numbers that are on the blue set on the top. So that's the procedure of making these quotients. And when I say a mixed quotient, I'm doing that same thing, except I'm limiting this coloring to require that adjacent sets have different colors. That sound good?
Yes.
Great. So let's return to this system that we had here. Remember, we had this number system where these were this additive system on the bottom. Remember where what was happening here is that in the first of these two sets, the even digits were 0, and in the bottom set, the odd digits were 0. And where did that set come from? Well, it came from taking every other set and giving them one color, and that would be this set. Whereas taking the other sets, the second, fourth, and sixth set, and so forth, those numbers together, that quotient would be there. So if I use the numbers only from the blue sets in the top, I create exactly the numbers that are in this one blue set on the bottom. And just to remind ourselves, what was the example? Just rewinding to the to where we had that. Oh, Jamboard does this to me sometimes. I don't know why. It seems to copy the wrong thing. Sorry about that. There we go. That'll make it happen the way I want. That was the example we had from the other page. I'll move it out of there in a second so we can see what we've got. So if we, whoever of you, I can't remember who gave me 64178345, it might have been Mishi. When we divided up in terms of the lower additive system is 601080400 and 4070350. And the first number is the one that we get through using all of the blue sets. And the second number is the one that we get from using all of the yellow sets. I think I just said that the other way. So let me fix it with some. So the ones with the blue are the ones that end, that have, there. This is the one that comes from the blue sets. Because if I say it wrong, I better fix it. And this is the one that comes from the yellow sets. It was that final zero that threw me off, I think. And that's true whether we look at the additive system on the bottom or on the additive system at the top. So another thing that's nice about the proof I gave of the structure theorem, so it was a different structure theorem, obviously I had to prove it from scratch, is that it also gave us a clue, and we can sort of see it's not really anything deep about, well, you know, let's say we were given the additive system here on the right. Oops. And if the question is, how do we find the British number system that gave rise to this? So how do we go backwards? You know, the structure theorem says there should be a British number system for which this is a mixed quotient. How do we find that British number system? Well, finding that British number system is actually sort of the easy part, and we can just talk through it. Well, some set in the British number system has to have 1. And so I look at this first set and I go, well, let's just stick into that first set, 1, 2, 3, 4, and that's as far as we can go because there's no 5 in this particular set. So we'll just leave 1, 2, 3, 4. And 5's got to be somewhere. So we look at 5 and we take as many as we can and we make that into the next set. So 5, 10, 15, 20. Our British number system has to continue with 25. So the next set will start with 25 and then what? Well, here's 25. 50 isn't in this set, so I guess 25 has to be by itself. So 50 has to start the next set. It's here. There's no 100, so 50 will be by itself. The next set has to start with 100. And 100, 200, 300, 400, 500, 600, they're all in that single set, so that'll be my last set. So that's the easy part of the structure. The proof of the structure theorem is how do you create, oh, and how am I going to color these? Well, I'll color the 1, 2, 3, 4 and the 50 the same color. Why? Because the 1, 2, 3, 4, and 50 are all in the same set. I'll color the 5, 10, 15, 20, the 25 the same color as the 100, 200, and so forth because they are in the same set. So the easy part of the structure theorem is, given an arbitrary additive system like the one on the right, how do you find the British number system and find the mixing quotient that should work? And well, that's sort of the uniqueness part of that theorem is, well, this is the only one that could possibly work. And again, I'm hand waving radically here. I don't pretend that this is a full proof. There is a tricky part of the theorem, and it's not so much hard as it just required a little bit of extra attention and care and saying things just the right way, it's easy to take a system like this and create a British number system and a mixing quotient. The trick is, why does that thing that we create actually equal this additive system that we started with? Again, it's not like it's incredibly deep, but why does the thing that we created look like this? Well, that was the hard part of the proof that I gave. So I have more things that I could say, but I also don't want to overwhelm, and I think this is probably a good place to stop. I want to just give a little hint as to where things went after this. This is most of what I had, or much of what I had to say in my paper, but I'm not even going to put that slide up for the moment. But where this went next is that, was it 2 years ago? I think it was 2018. I'm reading this article in the same journal. This was published in the American Mathematical Monthly. And I'm reading through this paper, and I'm like, something's ringing a bell for me. And the paper's about rolling dice and, you know, fair sacks of dice, whatever that means, and I'll explain what that means in just a second. And I'm reading through this complicated proof, and I'm like, it's ringing a bell. And I'm like, wait a minute, this person is more or less giving the same proof that I gave in my additive systems paper. It's just that he didn't have, this author wasn't talking about additive systems. He asked the following question, or a continued discussion of the following question. When can you have a fair sack of dice? And here's what he meant by that. We all know what rolling a die means, and for the purposes of this talk, this is a lot more, I'm almost tempted to take this off, but if you must read, you can probably listen and you'll get it better. The idea of a die is we're going to have a random variable where the results are non-negative integers, finitely many of them. So, you know, 0, 1, 2, 3, 4, 5, 0, 5, 6, 7, 9, 10, 11, whatever. And the idea of an unbiased die is that all of the possible outcomes are equally likely. And the idea of a fair sack of dice is when we add dice together, we get something that is itself unbiased, and specifically the outcomes are 0, 1, 2, 3, 4, 5, 6, 7, up to some number. So here's an additive system at the left, and ignore most of what's on this page. We all agree that this is a British number system, I hope. 1, 2, 3, 4, 8, 12, 16. 20 by itself, 40, 80. And this is an additive system of size 120, because if I add all of those numbers up, 3, 16, 20, 80, I'd get 119. So it's an additive system of size 120. And think about having a sack of dice where one die is equally likely to have 0, 1, 2, 3. One die is equally likely to have 0, 4, 8, 12, 16. One die is 0, 20, 0, 40, 80. It's the same numbers I had here, except I stuck in 0. And without, let's even forget I made this more complicated than I needed to. I'm going to take out the last two. If I had just those two dice, do we agree that the numbers from 0 to 19 are equally likely when we add the total? So this author of 2 years ago, Morrison, said, use the result that someone else had proved previously. If we have a fair sack of dice, each individual die is unbiased. And this author Morrison, whose proof looked, in my eyes, fairly similar to mine, realized, oh, we could have basically the same structure theorem. That same idea, his terms were, of course, completely different than my terms, and that's fine. But he came up with essentially the same results, where, so for example, here is the more complicated example. A die with these faces looks a lot like an additive system with these two sets. Two dice, and first die is 0, 1, 2, 3, 20, 21, 22, 23, and the other die is whatever I have on the bottom line. And with those numbers, we can get anything from 0 to 119. And using these two sets, we have an additive system of size 120, meaning you can get all the numbers from 0 to 119. So there's this remarkable correspondence between additive systems and fair stacks of dice, and then there's something about polynomials, but let's not talk about that. So this is my paper, this is Morrison's paper, and I really appreciate your attention. I'd be happy to answer any questions.
Thank you for a beautiful, lovely talk. And are there questions or comments? Don't be shy.
I have a question about using bases in the in his explanation. He mentioned that there were some bases in some of the sets, but I don't know how important that is for the whole proof.
Well, just to clarify, when I was using the term bases or basics, I can't even say the word right now. I was referring to things like base 2, base 10, binary, decimal, not bases in the sense of like linear algebra, just since we overuse some of these terms in math. And understanding, binary or hexadecimal or things like that, I find is sort of good inspiration for what a British number system is. Because it's as if a British number system just generalizes the idea of having bases, because no longer like in base 8 do we have the ones place 8, 64. Oh, I can't do my powers of 8 very far. But it's some mixing of base 8 and base 12, and the original concept of a British number system as De Bruyne envisioned it was mixing shillings and pence, where you sort of start in base 20 and then you move to sort of base 12 and maybe other bases after that. So I find it less useful to use, but definitely good inspiration.
Yeah, I see that. But you also use the money, the quarters, and which is kind of related to bases too in a way.
Yeah, it is, except, when we pass from quarters to dollars, we're no longer taking multiples of 5. We've gone from quarters to dollars, we've gone a multiple of 4, which is obviously neither base 5 nor base 4, because we started with 25. And so that's why I find money, as did De Bruyne when he said British number system, I find money to be a very helpful way of sort of figuring these things out, because we're all used to working with currencies. And most people who are reading my article are used to seeing US currency.
Yeah, that's good. And Melanie brought the idea of the first question that she was talking about them also. I guess modular arithmetic is part of it.
Yeah, modular arithmetic is a different way of attacking the same beast. It's just as useful. It's sort of just cutting it off at some point. And they're both very helpful ways, just two different ways of skinning the same cat.
Mm-hmm.
So in the Morrison paper, are the dice additive? I wasn't sure if that was a requirement.
Well, yeah, my definitions were hurried because I was trying to finish before 2 o'clock. Yes, when he speaks of fair stacks of dice, the definitions that he's using is basically, we have these random variables, and what we're interested in is rolling these dice and adding the results. That's his setup. That's what he's interested in.
Right, but is there more than one way to get a sum of the same sum, but with different combinations of dice?
Great question. So the Gussarch and Kruskal theorem, which I only summarized here, actually part of what they proved was answering exactly your question, which is that a given sum, and this is their theorem, this is not obvious, especially if you talk about unbiased dice, a given sum can come about in one and only one way. That's not obvious. It's not even obvious why they should be unbiased dice. Like, why can't I weight 2 different dice and get all of the totals that I want? Gussarch and Kruskal have a good proof of that, and which I won't try to say, but all I'll say is roots of unity, and throw that out for those of you who enjoy roots of unity, and you can look up the references. But it's not trivial, and so they prove not only that each die is itself unbiased, but also regarding your question, Steve, part of what they proved was also that each sum comes about in one and only one way. So.
Any other question or comment? Well, if not, let's thank the speaker again.
Can I ask a question, Wilfredo? Sorry, I didn't
Yeah,
raise my
sure.
hand before.
Yeah. Good.
Curious, because this is like really cool, and it does a lot for natural numbers. Do you ever do it for, like A plus IB style numbers, and we've got like two components and they don't interact with each other, but if you do different systems with them, it'll be extra exciting?
Yeah, I actually have not at all thought about that. I think those are there are probably some really interesting questions. I'll tell you what I have thought about, which is a little bit along the same lines, is every once in a while I read some article that makes reference to things like base -3. And every time I read this, I have to look again and see what that exactly means. But there are ways of expressing it in terms of sort of the ones place, the -3 place, the +9, the -27 place. And I definitely have in my mind, but haven't made into a paper or really thought about enough. Those all feel like you could take a British number system and shift some of the sets. And what you get is, instead of creating all non-negative integers, you create all integers. And base -3 or base -7 or whatever are particular examples of that. And I'd love to understand better, and maybe sometime I'll think harder about, like, is there a way of characterizing, like this characterizes all ways of getting non-negative integers. Is there a similar way of characterizing all ways of getting all integers? And I don't know, but the base -3 put together with the British number systems is bubbling around in my head and may or may not go somewhere someday.
Cool. Thank you.
I think actually the doing stuff in complex numbers is probably an equally interesting question, how those would interact with one another. My general sense of it is that you've probably asked a really hard question in the sense of maybe there is no structure theorem, or maybe there's a cool structure theorem waiting to be found.
It's a very equitable answer there.
Well, it's just
a lot of math.
Well, I mean, it's just a measure of my ignorance. It's like I have a feel for how this might go, but who's to say until someone actually thinks about it, which is the nature of discovering math.
Very true.
Okay, thank you very much.
Thank you.
Thanks.
Thanks so much for having me. I had a lot of fun. I hope you did too.
Well, I appreciate it. I have the illusion that I understood most of it.
You probably did. Don't sell yourself short.
Well, I got up rather late.
Okay, guys, so let's stop the recording, and I will send the